Sesim geliyor mu?
Geliyor hocam.
Ekran da gözüküyor değil mi?
Evet.
Okay, so last week we completed the signals and systems. Now we are going to move to LTIC system time domain analysis. Okay, guys. Okay. So the system can be a continuous time versus discrete time systems. Now, today we're gonna focus on the LTIC system, linear time invariant continuous time systems. And we can analyze this system in different domains, such as time and frequency and other domains. But today we're gonna look at only the analysis of such system in time domain. So LTI system, we have an input f of t and we have an output y of t. And the system is going to modify this or process this input according to the characteristic function of the system. So let's start with the introduction. First of all, we have an input and output. The input of this system and output of this system is related by linear differential equations. So we define the system equation according to the differential equation. And the typical generalized differential equation is given as follows. As you see, we have the coefficient, in this case is the 1 times d to the power of n times y of t, which is the output, plus another coefficient a n minus 1 to the power of n minus 1 times y of t plus, and so on, a1 times d, which is the differential, times y of t plus y a0 is the coefficient, time y of t. This is the left side, and we have the right hand side of the equation, which is bm of bm times differential m f of t plus bm minus 1 differential of dm minus 1 f of t plus b1 times differential f of t, and finally we have the b0 times f of t. These are generalized linear differential equations that show the characteristic of a system. In other words, it shows how the input f of t and the output y of t are related to each other. As you see on the left hand side, we have the y of t, which are the output, and on the right hand side, we have the input, which are the terms for the f of t. So here we use the notation of d, which is equal to the differential with respect to t, time. So capital D is a differentiation operator in this course. Okay, so we can take the y of t output as an out of parenthesis. Now we have the d of n plus an minus 1 times d n minus 1 and a1d plus a0. Let's call this as a QFD. QFD is a polynomial for this. And on the right hand side, similarly, we take the f of t out of the parentheses and we have this expression. So this expression is called p of d. Now we convert this differential equation in a compact form, which is given as follows. You have the q of d times y of t, which is our output, is equal to p of d times f of t. So this is called system equation. Of course, linear. As I mentioned in the last week, we are not considering any nonlinear system in this course. So in this case, the q of d and p of d are polynomials, as you see, and it has a degree of n, q of d, and p of d has a degree of m. So theoretically, these m and n can be any value, but practically m is less than or equal to n. Why? Because of the noise considerations in the systems. So why we need such analysis in time domain? Because most of the practical systems, they work in the time domain. And if you like to know the effect of an input to this system without going to the laboratory and to use this lab equipment in order to measure the output of such system, theoretically we can find the output when you apply a different inputs. So at the end of this course, you will learn how to apply, when you apply a different inputs to a system, how to obtain the output. So this is called a response of a system. So if I apply this input, what is going to be the response? In other words, the output of a system. So first of all, we split the response into two terms. A system can have a different two types of response. The first one is called zero input response, and the second one is called zero state response. So first of all, we need to find these two different responses, then add them up in order to obtain the total response. So then that means a total response consists of two parts. The first part is zero input response. The second part is called zero state response. Okay, the next question is, what is zero input response and what is zero state response? So let's start with the zero input response. As the name implies, is the system response when the input is equal to zero. So the name is zero input. So when the f of t is equal to zero, we look at the output, and this output gives us the zero input response. So let's think a little bit in detail. When I apply my input is zero, then what am I observing at the output of the system? So the output is the result of internal system conditions. So you just, because there's no any other result, right? And so as if you are pushing the internal system condition as an output, because there is no any input. In this case, so we obtain the zero input response. In other words, the zero input response is independent of external input f of t. So you cancel all the external inputs, and we just look at the effect of or impacts of the internal condition on the system. And this is called zero input response. The second part we said that is called zero state response. Zero state response is defined as follows: is the response, system output, when all the initial conditions are zero. Now we are doing the reverse operation. We are canceling all the initial conditions and we are applying an input. And of course we are seeing the effect of the input signal. So there is no any effect of the initial conditions, any internal effects. We are canceling all these internal initial conditions so that we can see the effects of only input signal on the system. In the zero input response, remember guys, we were canceling the input and we see the effects of the internal conditions. Now we are doing the opposite. We are canceling the initial conditions, making zero, and in order to just see the effects of the input signal. So then once we find out the zero state response and zero input response, and then we add them up in order to obtain the total response of a system. So this is how we analyze a system in time domain. Okay, after defining the total response as well as the its terms, zero input response and the zero state response, now the next question is, how are we gonna calculate the zero input response of a system as well as the zero state response of a system? So let's start with the first one, which is zero input response. Let's look at together how we determine the zero input response of a system. So we are going to call this zero input response as a y0 of t. So y0 of t is the solution of this, remember guys, system equation, which was a linear differential equation. And according to the definition, zero input response is obtained when f of t is equal to 0. That means I'm gonna plug in this f of t equal to 0, or replace f of t with the 0, and try to solve this equation. So I put it here, then the right hand side becomes equal to 0, and my left hand side polynomial q of d times y of t is going to be equal to 0. Okay, so let's expand this q of d, and as you see is a differential n plus a n minus 1 times differential n minus 1 plus a1 times d plus a0 times y0 of t, which is equal to 0. So zero input response is this. So I'm trying to find this y0 of t. So the question is how we are gonna solve this y0 of t in this equation. So let's consider the simplest case of the first order system when the n is equal to 1. Okay, so n is equal to 1. So then my general equation reduced down to this, which is a1 is 1 times d plus a0 times y0 of t. Then I expand it like this, d times y0 of t plus a0 times y0 of t, which is equal to 0. And then I take this term to the other side. Then my equation is going to be d times y0 of t is equal to minus a0 times y0 of t. So the capital D, remember guys, it was differential operators. So I replace it differential operators so that you guys can see, you know, differential of y0 of t with respect to t is equal to and how can we solve this equation is there are two ways. The first one is systematic way. The second one is the heuristic reasoning. So what this equation tells us is that what is the y0 is of such function that when you take the differential, you obtain the same signal or same function. Which function has a such property? Only exponential function has a such property. So when you take a differential of an exponential, you obtain the function itself. So the derivative of this has the same form itself. So therefore, let's assume that the solution is an exponential. So y0 of t is equal to c is a constant times exponential lambda t. So let's take the derivative of y0, the equation basically. If you take the derivative of this, you're going to end up with the c times lambda times exponential lambda t. Now that was equal to this one, means this. And in this case, y0 was equal to c times exponential lambda t. Then lambda is going to be equal to minus a0. So the solution for when the n1 is equal to 1 is going to be y0 of t is equal to c times exponential minus a0 t, where the c is an arbitrary constant. So that was the solution when the n1 is equal to 1. Now we need to generalize this solution to n. So instead of n is equal to 1, let's generalize this solution when the system equation has a nth order, d power of n plus a minus n1, dn minus 1, blah, 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 a1 times d, a0, and this. So when we generalize, there are two cases. The roots of this equation can be repeated or non-repeated. So the solution is going to be vary according to type of roots. If it's a non-repeated, we need to develop a solution. If the roots are repeated, then we have another different solution. So let's develop the solution for the first case, which is the non-repeated roots. So the general solution is going to be the general case of that was for the just one roots. Now we have this general solution, which is c1 times exponential lambda 1 times t plus c2 times exponential lambda t2 plus Cn times exponential lambda n t. So this is this general solution when the roots of the system are non-repeated. And we assume that lambda I, the roots are distinct in this case. And the constants C1, C2, Cn are arbitrary constants. How are you going to determine? Determined by the constraint on the solution according to the constraint or the initial conditions. Okay, so we replace the d with the lambda, in this case the roots. Now we obtain q of lambda. Q of lambda is equal to actually lambda minus lambda 1 times lambda minus lambda 2 times lambda minus lambda n. And this is called characteristic polynomial. So in this case, this equation is called characteristic polynomial. If I ask you guys to find the characteristic polynomial of system, you need to write down this. In this equation, lambda 1, lambda 2, lambda are called characteristic roots. And exponential lambda I t, where the I is 1 to up to n, they are called characteristic modes. So there is a characteristic mode for each characteristic root of the system. So for each characteristic root, we have a characteristic mode. Therefore, how can we interpret this solution? The zero input response is a linear combination of the characteristic modes of the system. So zero input response is as if we have a characteristic modes and we add them up, we come up with the zero input response. That solution was for what? That was for non-repeated root case. But the system may have a repeated roots. Then in this case, we need to develop another solution. So let's say we have a two repeated roots, which is d minus lambda time squared times y of 0 t is equal to 0. In this case, the system has a two roots and they are repeated. The solution in this case is going to be y0 of t is equal to c1 plus c2 times t times exponential lambda t. That was for the n equal to 2 or r equal to 2. Now let's generalize to this r case. When we have an r number of repeated roots in the system. This is the general case. And the characteristic modes for this repeated case are given as follows, which is exponential lambda t. The second mode is t times exponential lambda t. The third one is t squared exponential lambda t. And the last one is t power of r minus 1 times exponential t. So the solution, the general solution for the repeated root case then become as follows, which is y0 of t is equal to c1 plus c2 plus blah blah cr minus 1 times t to power of r minus 1 times exponential lambda t. So that is the solution for the repeated root case. If your system has a repeated, we use this. If it has a non-repeated, then we use this equation. Any questions so far? Okay, let's have an example. I'm giving you an LTIC system which has a system equation of d squared plus 6d plus 9 times y of t is equal to 3d plus 5 times f of t. So the question is determine y0 of t, which is zero input response. Under what condition? When the initial conditions is this and this. So this is a notation for the differential. If you have just one dot on top of the function, if you have a two dot, that means differential square. Okay. So that is the question for this given LTI system. Please determine the y0 of t under these initial conditions. Okay, how we're gonna solve this problem? First of all, in the first step, I need to find the characteristic polynomials by replacing the d with the lambda. So d squared plus 6d plus 9, if I replace it, my system characteristic polynomial becomes lambda squared plus 6 lambda plus 9. This is called characteristic polynomial of system. Now, the first step after this, the second step is to find the roots. In this case, the roots are plus 3, right? Lambda plus 3 times lambda plus 3. So lambda 1 is minus 3, lambda 2 is minus 3. That means the system roots are repeated. Then I need to use the appropriate equation, the solution for that. So the characteristic mode are in this case is exponential lambda 1t and lambda 2t. Since they are equal to each other, is going to be exponential minus 3. So the general solution for the repeated root case, if you guys remember, it is for the two roots, c1 plus t times c2 times exponential lambda t. Now, let's plug in what we know. We know the lambda, and we plug in here, and our equation becomes y0 of t is equal to c1 plus t times c2 exponential minus 3. So what are the unknown parameters in this case? Is this lambda and is this c2 and c1 constant? If I find these two constant and plug in here, then I can determine the zero input response. Okay, how we are going to find this? Sorry. To find a unique solution, we need to determine the C1 and C2. How we're going to determine these constants is using the initial conditions that are given in the example. So the first initial condition was y0 when the t equal to 0 is 3. So y0 when the t equal to 0, if I put a t here, then the C1 is left, right? And this becomes 1 and C1 is equal to 3. From the first initial condition, we found the C1, which is equal to 3. Now let's use the second initial condition, which is the derivative of y0 of t, when the t equal to 0 is equal to minus 7. So first, let's take the derivative of this. If I take the derivative of this, is minus 3 times c1 plus c2 times t plus c2 times exponential minus 3. After derivative, if I replace t with the 0, this t is gone and this becomes 1, is minus 3, 1, c1, minus 3 times c1 plus c2 is equal to minus 7. And I know that c1 was equal to 3, minus 3 times 3 is minus 9. If I take to the other side, c2 is equal to 9 minus 7, which is equal to 2. Now, I determine the last constant, which is c2. Now we are ready to plug in these values to this equation. So I put c1 as a 3 and c2 as a 2. Now I end up with the following zero input response, which is equal to 3 plus 2t times exponential minus 3t. So that is my zero input response. This is how we determine zero input response of a system. Any question, guys? Okay. So another topic, important topic, is unit impulse function. This is used, unit impulse function, unit impulse response. Remember, guys, last week we learned some useful function that we're going to use. One of them was unit impulse function, which we call delta function. And according to the definition, delta of t is equal to, it has value, non-zero value, only at t equal to 0. And for the remaining values, it was equal to 0. So this is an important function that we use in order to find the unit impulse response of a system. So delta of t, this impulse response is used, impulse function is used to determine the response of a linear system. In practice, which we call reverse engineering. So you got a black box. It can be a device that you obtain, and you want to learn the behavior of this system. So one way to do that is to use a reverse engineering to understand the behavior of this system, so which we call black box. And one way to find the impulse response of these systems is to apply delta function. So when you apply delta function, as if you are multiplying the h of f in the frequency domain. So that means as if you are pushing this h of t to output. So that was an unknown function. When you apply a delta function, as if you are pushing this to the output. So the output is going to be h of t. And this is achieved by applying the delta function. And you apply a delta function to a system, you obtain the impulse response of that system. So the question is how you're going to find this impulse response. For an LTIC system, remember that was the general linear differential equation. In this case, h of t, which is the impulse response, is given by this equation. H of t is equal to Bn times delta of t plus P of d polynomials times y0 of t, remember guys, was zero input response, times u of t. That was unit step function, if you guys remember. In this case, Bn is the coefficient of the nth order in the P of d polynomial. And initial conditions are for for all of the initial conditions equal to 0 except y0 derivative of n minus 1 is equal to 1. Under this condition, we obtain this h of t. So we are going to use this equation to find an impulse response of a given system. Okay, let's have an example. So the question is, we are given this system equation, which is d squared plus 3d plus 2 times y of t is equal to d times f of t. So the question is, determine the h of t. In other words, the unit impulse response of this system. Okay, so the solution, we are given this, we are going to use this equation. H of t is equal to Bn times delta of t times P of t times y0 of t, unit impulse function. Sorry, y0 of t is a zero input response times the u of t. Now, here we have three unknown, right? The Bn, P of t, and y0 of t. So according to this, that was the P of t was equal to d, right? And the Q of t was equal to d squared plus 3d plus 2. How do we determine the Bn? First, we need to find the n. N was the maximum power of Q of t. In this case, the maximum power is 2. That's why n is equal to 2. Okay, and the Bm, remember, it was Bm times dm plus b1 times d1. In this case, since the P of t is equal to d, that means b2 is equal to 0 and b1 is equal to 1. So my b2 is equal to 0 because of this, guys, if you remember. In this case, b2 because is this and b1 is 1. So that's why P of t is equal to d. So we got the n from this Q of t power, and the b2 is equal to this value. Okay, so we found the P of t, we found the Bn, and what's remaining is to find the y0 of t for this system, which was the zero input response. How do we find the zero input response? The first step was, guys, to find the characteristic polynomial first using Q of d. And by replacing the d with the lambda, we obtain the Q of lambda, which is equal to lambda squared plus 3 lambda plus 2. The second step, we need to find the roots, right? Roots, in this case, is plus 2 and plus 1. So that means the roots are equal to lambda plus 1 times lambda plus 2. And lambda 1 is equal to minus 1 and lambda 2 is equal to minus 2. Since they are not equal, so these roots are non-repeated. If the roots are non-repeated, then we use this solution, right? That's the general case. And we need to use for the two root case, which is equal to C1 times exponential lambda 1t plus C2 times exponential lambda t2. Okay, so these are zero input response. And we know that lambda 1 lambda 2 from here. What are the unknown is C1 and C2 coefficients. So according to the, we need to find these coefficients using the initial conditions. And the initial conditions was given in this definition, guys, if you remember. All the initial conditions are 0 except the one with the maximum power. So that means in this case y0, 0 is equal to 0 because n is equal to 2 in case. 2 minus 1 is 1. So the first derivative of 0 state, 0 input response is equal to 1. 1 the t equal to 0, of course. Okay, these are our two conditions, initial conditions. Now we are ready to obtain the C1 and C2 using these two initial conditions. Let's start with the first initial condition. Y0 t is equal to this. When the t equal to 0, we just plug into 0, 0, and it becomes C1 plus C2 equal to 0, and C1 is equal to minus C2. Now the second initial conditions is given by this. The derivative of 0 input response with respect to t. Let's take the derivative together. This is minus C1 times exponential minus t. If I take the derivative of this term, I obtain minus 2 times C2 times exponential minus 2t. So that's my first derivative of 0 input response. And I'm going to evaluate this result when the t is equal to 0. And according to initial condition, this is going to be equal to 1. So let's plug in this 0 together to here. And we end up with a minus C1 minus 2C2, which is equal to 1. And by using this equation, you can solve, and we end up with C1 to equal to 1, and C2 is negative of that, which is minus 1. So we obtain these two coefficients for the 0 input response. And we plug into this equation, C1 here, times exponential minus t plus, minus 1 times exponential minus 2t. And you reorganize, so which is going to be equal to this. So we are not done yet, right? That was the last unknown in the equation of h of t. So the b2 was 0. This term is gone, is cancelled. We have the p of t, which is equal to d times this y0 of t that we just obtained together times u of t. So that capital D means differential. We take the derivative of this, which is equal to minus exponential minus t. And if you take the derivative of this, minus 2 come to here, minus times minus 2 becomes plus 2 exponential minus 2t times u of t. And that is my exponential terms. Sorry, this is my impulse response. Any question? Okay, let's have a 15 minutes break. We'll come back after 15 minutes.